All right, guys, so today we're going to talk about kinetics. And with kinetics, the first thing that we need to talk about is collision theory. And so, collision theory and how we're going to relate to it is with chemical reactions. Chemical reactants will need certain things to occur in order to chemically react with other reactants. And so, in order to react, reactants must first, and this seems oversimplified, but they first must collide. There must be a collision between two reactant particles in order for a chemical reaction to occur. They must come in contact with each other. They must also collide. When they must collide in the proper orientation or geometry. Not every reactant particle colliding with another reactant particle collides in the proper orientation. They must collide in the proper orientation. And they must collide with sufficient energy. They have to have a sufficient or a minimum amount of energy in order to cause the reaction to occur. Otherwise, the particles just bounce off of each other and they don't actually chemically react with each other. Now, sufficient energy is going to greatly depend upon temperature of the reaction, and so temperature can affect that. And then this is also going to relate to activation energy, and so that is a term that we're going to learn here in just a second, activation energy. And so you need to know that these postulates to the collision theory. So for a reaction to react, reactants must collide. They must collide with proper orientation or proper geometry, and they must collide with sufficient energy to cause the reaction to occur. Now let's define activation energy. And so you're going to see this in chemical in formulas as E sub A, the energy of activation. So activation energy is this. Activation energy is the minimum amount of energy required for two colliding reactant particles to chemically react. It's a minimum energy needed. They have to have this energy in order for them to react with each other when they collide with each other. And now let's go ahead and define what temperature is. If you ask the general person out there, hey, what is temperature? You're probably going to get an answer like, well, it's hot or cold. It's how hot or cold something is. Well, that's not really what temperature is. Temperature actually has a very specific definition in science, and it's a measure of the average kinetic energy of all molecules or atoms of a substance. That's what temperature is. It's a measurement of average kinetic energy. And we're going to use, for average kinetic energy, we're going to use AKE. So average kinetic energy is a measurement of temperature. Now, you should, at a very minimum, have a basic understanding of this already, because you know that if you rub your hands together, friction creates heat. You know that if you heat something up, you know that the particles in that substance begin to move faster. Okay, and so temperature is a measurement of motion, of how fast particles are moving. That is what temperature is. The slower the particles are moving, the colder the temperature. The faster the particles are moving, the higher the temperature. Now, we don't need to actually go into the kinetic energy equation as far as a requirement, but I want to briefly discuss it because I think it helps you understand and answer questions with temperature. So the kinetic energy equation is 1/2 mv squared. To make it simple, because we don't actually need to do any calculations with this equation, I'm going to ignore the half and I'm going to ignore the square here. And so effectively what we have is we have a kinetic energy equation that relates mass and velocity to each other. And the relationship between the mass and the velocity here is an inverse relationship. For the kinetic energy to remain constant, if the mass goes up, the velocity must go down. That's the kind of relationship that we have here. And so if you have two substances or two gases, let's say we had two gases, and we had gas A in a container, and we had gas B in a container, and the gas A substances were massive substances or massive molecules, and the gas B molecules were small molecules. They were not very massive. And these two items were at the same temperature. T1 equals T2. They were at the same temperature. How would the motion of the molecules of A compare to the motion of molecules of B? Well, if the temperatures are the same, that would mean that the kinetic energy of A equals the kinetic energy of B, or the average. We should be correct here. The average kinetic energy of A equals the average kinetic energy of B. Well, then that means that the mass of A and the velocity of A is equal to the mass times the velocity of B. Well, if we have a big mass here and we have a small mass here, then how do the velocities compare if these two things are ultimately equal to each other? Well, the large molecules, the massive molecules, will have a low velocity, and the small molecules will have a high velocity. And so that's an important little concept to understand in regards to temperature, is how the kinetic energy causes the speed of the molecules to vary with their mass in order for them to be the same temperature. So an important thing is that two substances at temperature 1, temperature 2, if those temperatures are the same, that means that the average kinetic energies of those two substances are the same. That's an important point to remember. Now this also brings me to a graph that I want to show you called the Maxwell-Boltzmann curve. And so this graph is going to have a number of particles on the y-axis, and it's going to have energy or kinetic energy on the x-axis. Now, if we took this this box back here that we had, and inside that box we had a whole bunch of gas molecules, and it was at a certain temperature, well, that means the gas molecules in that box are all moving. Now, the question is are they all moving at the same speed? Well, they're not. Some are moving fast, some are moving slow. They're not all moving at the same speed. And so if we graphed the number of particles with a particular kinetic energy, with low kinetic energy over here and high kinetic energy over here, well, you would find that you would get a graph that would look something like this, where you would have some molecules that have low kinetic energy, that are moving slowly. You have some molecules with high kinetic energy that are moving fast, but the vast majority of the molecules have a medium kinetic energy in relation to the others. And if you took all of these molecules together and you took it and you found the average kinetic energy, well, you would get a point slightly to the right of the top of the curve. And it's going to be slightly to the right of the top of the curve because we have this long tail off on the high side that kind of shifts the data to the right. And that point right there, that is going to be the average kinetic energy of this substance, which you already know is related to or equal to directly its temperature. And so a particular average kinetic energy is related to a temperature. You could actually graph out, a table, AKE versus temperature. And if some molecule has a particular kinetic energy, it would be equal to 50 degrees. And another one would be 51, another one would be 52. So whatever that AKE, it is the temperature of that substance. So that's going to be your intro to kinetics. All right, so let's just do a quick review of what we looked at today. And so kinetics, that's what we're talking about, kinetics, collision theory, 3 postulates. You know these postulates. For a reactant to react, you must collide with proper orientation and sufficient energy, which depends on temperature and relates to activation energy. The activation energy is the minimum amount of energy required for 2 colliding reactant particles to react. Temperature is a measure of average kinetic energy. And the Maxwell-Boltzmann distribution curve, which is a graphical representation of kinetic energy versus number of particles.